Saying that I'm going to continue with the introduction that Javier did for fluid mechanics. In particular, he said the main equation that we are using, the Navier-Stokes equation. And when the viscosity is 0, then the Euler equation. He mentioned several properties of these equations. In particular, he talked about the flow, the particle trajectories, some consequences about the incompressible condition. And then in the second and third lecture, he focused on the Euler equation. And he explained how to find a different formulation, the vorticity stream formulation, to remove the pressure. And prove that, assuming that solution exists, then they have a continuation criteria, they will cut on market. So today what we are going to prove first is that the Euler equation is so this is today. This is approximately the chapter 3 of the book Mind Over Touching. Then on the next lecture, and by the way, next week there are no lectures, so we will continue on the following Monday, on Monday, May 2. On the second lecture, we will prove the same local existence and uniqueness, but for Navier-Stokes, and I will make some comments on the rate of weak solutions for Navier-Stokes. So here everything is going to be classical, that is, the solution will satisfy the equation pointwise in x and t. And on the following day, I will comment on weak solutions for Navier-Stokes. Then I will make an introduction of some technical steps. In particular, I will talk about Littlewood-Paley decomposition. Best of spacing. And very standard estimates of partial differential calculus. And as an application of these tools, we show the global existence of solutions in critical spaces, that is in the borderline in terms of the for Navier-Stokes. So I will give another definition of solutions, mild solutions. To Navier-Stokes. In spaces with critical regularity. And depending on the time, because I don't know if this will correspond to exactly one lecture or not, on the last 2 days or so, I will comment on a variation of the Navier-Stokes when we have density that is not constant, the so-called inhomogeneous Navier-Stokes. And although the density will not be constant, I will still keep the incompressibility condition. So I should say incompressible, inhomogeneous Navier-Stokes. And I would like to show a result which is now about 4 years ago, but there are still some work in progress about different people. in homogeneous Navier-Stokes where the density is a part. And here's the density part. So basically, when we have two fluids, each one with a different density. Okay, so let's start with the first one. It's uniqueness and existence for rows. I have them written. Or this one plus the incompressibility condition and some initial data. And some boundary conditions that in general will be decay of all the quantities at infinity and with sufficiently fast decay. So I will just write here that all the quantities go to zero. And I think Claudia and probably Jamin already commented that here we don't have initial condition for the pressure. But in fact, the pressure is given in terms of U. So I will just repeat how to obtain the pressure in terms of U using the so-called array project. So because we have the incompressibility condition, if we take the divergence of the first equation, we immediately obtain that the pressure satisfies this Poisson equation that I'm going to write using indexes. Now we invert the Laplacian in the whole space with the decay boundary condition. Because this is divergence free, I can move the derivative outside. Okay, so the pressure is given by the double Riesz transform of the product of the velocity. Okay, the Riesz transform is just a Fourier multiplier of order 0 that we can see here. Okay, so now I'm going to put back this expression into the Euler equation and obtain a formulation without the pressure. And also, I will still use a component form. I will have partial T of UK plus UK partial K UI plus partial K, and now the pressure. And I will write all this as an operator acting on the convective part on U graph U. So this is plus, I will write, I want here, sorry, this is the case. I want the same quantity here and here. So this is the Kronecker delta plus all this apply. So removing again indices, we have that the Euler equation is partial PU plus this operator that I'm going to denote P, the direct projection, apply to U. Here, E is the operator identity plus all this, okay? Yes, from here. We call it Euler projector because by construction, what we are doing is that when we apply P to a function, we have the same function and we have removed all the part that has non-zero divergence. We did here, we took the divergence of the equation and whatever we find, then we are removing from the original part. So P takes a function and projects it into the part with 0 frequency. And from this expression, some remarks that we will use many times today. This is a Fourier multiplier of order 0. So this is the identity. Because it's a Fourier multiplier of order 0, it commutes with derivatives. It's self-adjoint in L2. And well, I already said if a function is divergence free, then P of U equals U. Okay, so the expression I will use, for the Euler equations is this one plus the initial data. And now we don't need with U0, let's say, I will denote L2 sigma, the space of functions that are in L2 with 0 derivatives. So now the incompressible condition, it's only placed on the initial data, but because here we have the Leray projection, this guarantees that this is divergence free. So for all time, the solution is divergence free. Okay. Let's take the theorem that I want to prove today. Let the initial data belongs to HS sigma, where again sigma simply means that the function has divergence 0 with S, so the number of derivatives bigger than dimension over 2 plus 1. Well, I should say, I haven't said it in any place where the functions are defined, but I'm assuming like in the other lecture that U is a function of xt and goes from Rd to Rd. Okay, so this is the dimension. I will not consider bounded domains, and also I will not consider like periodic boundary conditions. For periodic boundary conditions, everything we are going to do is almost the same, but for bounded domains, it's different and harder because we are going to use a lot of Fourier in all the estimates. Okay, so in this case, let's use a 0. Then there exists a time and a unique solution that belongs to this space, continuous in time, and with values in HS. C1 in time with one derivative less. Okay, so before going to the proof, just mention that this theorem is very standard. The first proof dates back to 1925 by I don't know how to write this, something like Liechtenstein. Okay, I'm just going to write Lee. And then Cato, this is only for an integer number of derivatives. Then Cato and Ponce in the 70s and 80s. And there are many other variations, as I say, in bounded domains and different conditions. Also that the result is also true in many other spaces, not just in this overlap space. If we change, so these are S derivatives in L2. If we change the integrability, we can obtain the same theorem in a much bigger family of spaces that I will define in the future lecture. These are best of spaces. But just to say that these are S derivatives in LP with some refinement, some other coefficient. If the embedding into C1 hole. Okay, so this is the only condition that matters, and this is why we have this condition here. Okay. But it doesn't hold in the limit case. So when S is equal to D half plus 1 in sublevel spaces, then the problem is ill-posed. This is resolved by Burgen and Lee in 2015. And also, it's ill-posed in CK for any integer k bigger or equal than 1. And this is also by Burgen and Lee in 2015. And El Guindi and Masmoudi, almost at the same time, but the paper is published in 2020. Okay. And I will not mention any about this because, in fact, I don't know the proof. So let's do the proof of this result. So the proof follows a standard method to show existence and ubiquitous of solution. The first thing one would try, or the easiest thing is if we can find some way of write the equation as a fixed point and use a fixed point theorem, then we are done. We have the solution and everything. Many times that is not possible, like here. So then we first modify the equation, so we construct a family of regularized problems. So we call those problems epsilon is the parameter. And I introduce here a modifier. And also we modify the initial data. And for this equation, we show the system and uniqueness. And in this case, we can use a fixed point argument. Well, here by modifier, I will be using Gaussian kernels. So P epsilon S. I prefer to think of it in Fourier. It's just this Gaussian. And in particular, in X, the one norm is just a constant. And well, a standard things about modifiers. Then the second step, once we have a family, like a sequence of solutions, each one of them might live in a different, for a different time t epsilon. So we want to show that all of them share a time interval. So I will show in particular that t epsilon can be taken as infinity. So all the regularized solutions are global. Once that we have this sequence of solutions, we want to extract some subsequence, or we want to show that they converge to something that solves the Euler equation. And for that, we will need some uniform bounds. We will show that the sequences is uniformly bounded in epsilon. In HS. So we will show that there exists a time independent of epsilon, such that there exists these uniform bounds. What else? Once we have the uniform bounds, we will show convergence. And here again, depending on the problem, there are many different possibilities. One can use some kind of Aubin-Lyon's theorem, but for this case, we will just show that the sequence is Cauchy in a lower regularity space. And by the uniform bounds, it will inherit this regularity properties. Okay, so we will have a strong convergence in this space with this uniform bounds. And finally, we will want to show that the limit object of the original equation is unique in its class and continues in the partial differential. So now I will go over each one of these points and the proof will be concluded. I might skip some part in the last step depending on the time. So for step one, I more or less already mentioned that we want to apply some fixed point argument to this regularized system. So I will define this function equal to all this here. Well, let me introduce notation. So to avoid writing all the time the modifier like this, I'm going to write the modifier operation like this. So now defining the right-hand side. Like this, so that the Euler equation can be think of as an ODE on a binary space. Vale. Okay, so to use a fixed point theorem, in particular Banach fixed point theorem, I want to show bounds on F. I will first show that F epsilon is bounded in HS, bounded on Lipschitz So let's perform the estimates. This is equal. Because of the divergence free, I can put the gradient outside. Now, because we have the modifier, well, I will write this in Fourier. Well, the Leray projection, we said that it was a 0 or the multiplier, so it just disappeared. And the modifier, I said that is going to be this one. Okay, and I want to get rid of the modifier, so we just use that this quantity. Is less or equal than constant. So basically, the price to pay, we want to bound the derivative without putting more derivatives in U, because the modifier is like a cutoff at frequency epsilon. To bound it, we just need to pay a price of 1 over epsilon. And we can see it here. We basically put here epsilon and epsilon. So all the first term is bounded. Epsilon to the -1. And then what is left is J epsilon U in HS. And now because S is bigger than the dimension over 2 plus 1, we have the embedding. So we have that J epsilon U. Well, we have that HS is an algebra. Okay, we have the embedding in elliptic. Yes, okay. And this last step again is using the properties of the modifier. Basically, that the modifier is bounded in the Fourier transform of the modifier is bounded in L infinity. Okay. Now to prove that its Lipschitz is almost the same. this part is common in both terms. Now we add and subtract. And by the same reason as before, we obtain the bound C epsilon minus 1. In the first case, U, in the second first, B. Times human. So we have obtained that it's Lipschitz in this space. And finally, with these bounds, we construct the fixed points. We write the Euler equation that we have it there. U epsilon t equal to some functional E epsilon. Which is okay. Okay, so let's do the ball. I will apply fixed point theorem on this with the ball of radius r equal to twice the size of the initial data. And for a time, I think we need here the constant should be the same as this constant here and this constant here. Right. And the ball where we will apply the fixed point theorem is just continuous on this time interval, the closed ball on the space HS with radius r. And well, I think now from here it's clear the estimate that follows. We have basically now repeat the estimate that I did in this space for this function. And you will obtain here the HS with multiplied by t, and that's why these numbers were chosen. Okay, so with this, we obtain the uniqueness and the system in this time intervals of our solutions in HS. And something that I was missing to say, once we have obtained U epsilon here, it's immediate to obtain that the time derivatives is in L infinity with one less derivative, simply because I just remove it, sorry. because the time derivative, can you see here? Yes, is given by this f, and this f was, it has a derivative, so it loses one derivative. Okay, now let's show that all the regular solutions are global. Yeah, so because, well, I will apply a theorem that I'm not going to mention or prove, but if we have an autonomous, I think it's said that, ODE, then to continue the solution in time, we only need to show that the norm is controlled So this is the only thing I will need to, that the solution doesn't need our state. Vale. Well, I'm going to show first the L2 norm and then the homogeneous HS norm. So for the L2 norm, we will need this later. I'm going to obtain a uniform in epsilon bound just by taking L2 inner product here. This was the array projector. I'm going to write this in component for a second. So this is J partial J U I U epsilon. Now the array projector, I said that it was a Fanjoy, so it moves to this other side. Same with the modifier. Now this is the gradient free, so we can remove the projection. And now we have here the derivative of something multiplied by something. So these two things are the same. So this is equal to 1/2 J epsilon U epsilon times gradient of J epsilon U epsilon squared. And this is the main trick that appears many times along the proof. Now, this is where we are using the structure of the equation and the flow is in compression. We integrate by parts. So this is exactly equal to 0. So we have obtained that U versus T L2 is equal to equal to the initial data, and this is it. This is equal to that. So we have obtained a uniform bound for the L2. And now we have to do another estimate for the HS norm. But here we don't really need the bounds to be uniform. Okay? The first one is because it's simple and we need it. So for the HS norm, I will use the formulation that we have here. I'm not going to copy. I'm going to use this formulation and estimate the HS norm directly from there. Plus it is bounded by the initial data. And this we can be very rough. This is T. The modifier and the projection, let me say, yes, disappear. Like I can even do like before. Extract this out, so this gives some epsilon -1. And this we did it before. It's less or equal than u epsilon. Less or equal than this. And now the thing is that I want to obtain a bound that doesn't depend on the HS norm, but this is less or equal than, using that we have a modifier, we put the derivative on the modifier, we pay a price of epsilon to the power s, and then 2. So in the end, all this is less or equal than HS plus T C epsilon -1 minus 2s. It doesn't really matter what the constant is. The thing is that for every fixed epsilon and fixed T, we have a bound. So the solution can be continued for all time in capital T. Vale, so now the step 3, we want to prove uniform bounds. We already have the 2 uniform bounds, so we now need to do this one that here we've done very badly. We want to do the same with a bound that doesn't depend on epsilon. Okay, some constant independent of epsilon. We have this one. So we just need to bound the homogeneous one, which is defined in Fourier. So I will do another energy estimate. Let's take here inner product in H. So this with U epsilon in H dot S. I write the definition of this. This was the relay projection, the modifier. J epsilon to epsilon gradient now I already did before. This we move it to the other side. We use that U is divergent free, so disappear. And we obtain this expression. And we want to say this claim that all this product here, and I will forget about the modifiers for a moment, so I will just say that U grad U times U it's S is less or equal than some constant U HS squared gradient of U in L infinity. It's not completely trivial because in principle we have S derivative applied to one derivative. So one should expect here more than one derivative. So I will assume that we have the claim. Later we will prove it in some cases. And let's continue with this. If we have this claim, then this is less or equal than C U HS squared. And now gradient of U in L infinity, because we have this condition. Well, I will just keep it here, but I will remove it in a moment. We have this is bounded by the HS norm. Let's join this inequality with the L to 1. So we have concluded the non-homogeneous HS norm is less than equal to some constant the power cube. Let's remove one of them. So take the derivative here. Basically, all this ODE. Or in other words, we have an ODE, we can solve it to obtain the time interval for the solution. So we have the U epsilon HSP is less than equal, this is, I think it works. Well, it's integrating this one. Yeah, I think it's like this. Let's call it this one P U HS. I think it's something like this. Okay, so we have the bound for sample. So choosing P0 in this form, we have that. Okay, so we have the uniform bound that we were looking for. So we only need to prove the claim. Well, in step 3, I said, well, yeah, I read the uniform bound in this case. Okay, perfect. And for the derivative, as before, okay, we just lose one derivative. Okay, so let's prove the claims. I will do 2 cases for the claim. I will not prove this in full generality for general real number S, but I think that maybe we can do that, or you can do that once we do little good Bailey decomposition and these things in the following days. So today I will do this for integer derivatives, and in the case of real derivatives, I will prove a weaker estimate that it's also enough for our purposes. So the integer case. Well, the integral case is quite direct. It's just writing what this is, using just one trick that we have already used it sometimes, and then using some interpolation inequality, like a linear inequality that I will just state and use. So this is equal to, I have to write the derivative, so partial alpha, so any derivatives up to order n of u grad u times alpha derivatives of u. Now the product rule. So beta derivatives on u. And again, the reason why we can't close the estimate is that in the worst case, in the most singular case, when beta is equal to alpha, this term will cancel. For beta equal to alpha, we have, I think I wrote it wrong, is the opposite one. Yeah, so this, okay, let me just change it to have the same as I have. And B. Okay, so here this is the most singular because we have alpha derivatives plus 1. So in this case, we have u gradient partial alpha u, which is equal to 2. So in this sum, we can remove that case. Some big constants. Okay, so we have, I'm just going to write the derivatives like this. We have m minus g derivatives applied to u. Then we have j derivatives from beta and m derivatives. This is a finite sum, so we just bound it by a constant. I will put this term in L2, so we already have u HM. And then we have the other part in L2. Let me write this also like this. So -1 gradient U. In L2. And now is where I'm going to use some interpolation. We have here the L2 norm of some powers of derivatives, and I want to bound it by L2 and L infinity. So this I will just copy it. I'm going to use this estimate, Galiardo, Nuremberg, Sobolev inequality. And this one I very likely will prove it as an exercise in the general case using Littlewood-Paley decomposition. Here I will just state it for integer. And okay, we're just playing with the numbers, matching the numbers here and there, and adding all the powers. One obtain that. The estimate. This is just right here, K and I equal to whatever we have here. Oh, I'm missing one step. Okay, so maybe okay, so from the L2, put this in some LP, this in some LQ, and later, for each one of them, use the Sobolev interpolation and match all the numbers. And now I will prove the other case when S is real. And this is nicer. Instead of gradient of U in L infinity, which is also true, but I don't know how to prove it right now, I will use this polynomial, which is weaker, but it's enough because this is also less than like the embedding point in this case. But well, the proof of this is much more direct. Write this in Fourier. So this is a convolution. And now we have to do in the end the same as we did before in Fourier. We have one more derivative than we can allow. So we have to use that trick that this structure, having this and this, cancels one term. So we have to introduce it here artificially. I will add something that is 0. And what is 0 is this is the part coming from gradient u, and this is the u. So I'm going to add here S derivatives. And this this term here is 0 by the divergence property. Okay, we have the function and the gradient of the same function. So all this is equal to 0. And you can make the computation writing it in component 4 or just going backwards to the physical space. So then let's subtract this quantity to what we have. So basically the difference between this and this is just chi to the power 2s minus this product. Of this time. Yes, minus. And I've only taken one, so there is another one. The other edge. And now here, one can use apply the mean value theorem to this function, to x to the power s, and approximately what we get is a factor of eta and then a factor of the other terms with one less derivative. This is still not good because here we have chi and we want to distribute it out of this u, so we want to put it here, but again using the triangle inequality. With a different code. Here this is this plus this. Okay, just from the triangle inequality, writing C. So now from here, I put this in L2. And now we have the L2 of the rest, which is a convolution. So we have the L2 of u eta times derivative of u and let me put it. We have a factor of eta here. So eta and these two. And now we are almost done. We have the same function here. This is one derivative of u, one derivative of u, and the same power here. So when basically this is the same estimate for this or for this, applied to one factor or to the other. So let's look at this one. When the eta s minus 1 hits here, we get eta s u eta, and this one untouched. So now the L2 norm of the convolution the L2 norm of the convolution is L1, L2 by Young's inequality for convolution. So L1 of this quantity, so this is the factor there, gradient of U Fourier transform in L1 and another factor of. Vale. So this was step 3. We have this uniform bounds. I'm going to write here the estimate that we have. And now let's show the convergence. So now we want to obtain a limit, and in the next step we will want to obtain that the limit solves the equation. And we said that we were going to do this by showing that the sequence is the Cauchy. In a lower regularity space. So let's assume that this is true. That is that okay, that the vale. So the estimate that I have is that U epsilon minus U in L infinity 0 T0 L2 goes to 0 as epsilon versus. And I also have the uniform bound that I wrote there, or the higher norm HF. So now I'm going to interpolate the norms in the middle with this one and that one there. I'm not proving the claim so far. I'm just using the claim to show that not only we have convergence, a strong convergence in L2, but also in all the Sobolev spaces up to HS without including HS. This part is bounded from the uniform bound, and this part here goes to 0. So this is basically the idea that we have also a strong convergence for some U epsilon going to U in an infinity HR with R less than S. We will need this because in the nonlinearity, when we want to show that the limit object is a solution, we have U grad U. So we will need a strong convergence for graph U. Here, S was bigger than dimension over 2 plus 1. So in particular, dimension is at least 2. So this is bigger than 2. So in particular, from here, gradient U minus gradient U epsilon near infinity. This also goes to 0 as epsilon goes to 0 because we have more than 2 derivatives. So we can choose R bigger than this quantity and smaller than this. Okay, so I think I will prove the claim that the sequence is Cauchy. And then it's almost done. We only need to prove the last step, which is that the limit actually solves the equation, which is a short estimate. So let's prove this claim. And I will prove it in the following form. We will show that let me check submit. So it's just performing the estimate and using all the regularity properties that we have before. Here it says U epsilon minus U delta in this space is bounded by the minimum of epsilon delta times the norm of the initial data. So I will estimate this difference here. So let's take the equation. U epsilon now take inner products with the difference, and we have that. Equal. Now let me write what is this difference. All the time we are going to look for some difference between epsilon and delta. So we need to add and subtract some terms. So this was the projection modifier. And U graph U. Okay, maybe I should mention before. So my goal is to prove that this is Cauchy, so I want to obtain that all the terms contain a difference or a term which is epsilon or delta. No? So how I'm going to obtain that? Well, we use that we have the modifiers and that the modifiers are smooth, in particular they are Lipschitz. So when we have difference like this, in say some sort of space, then we can bound this by the minimum of this parameter obtain one derivative for S. Basically, put the derivatives in. Yeah, put the derivative. Sorry, apply the main value theorem and move the derivatives to F. Yeah. Okay. Well, so with this in mind, I will write this term, looking all the time for difference between the modifiers. So let's start. This is E. Now I've added this one, so I've subtracted this one. I have to add this one. I want to do it. Yeah. So this one. Now we change this. Here, J delta. Now I do the difference between U epsilon and U delta. This one, U delta times. Here I'm forgetting. Yeah, in all this term, there should be a JS, all right? So now. And these are all the terms. Okay, and now we have to bound all this term. We are here. So all those terms here, put them back. And now we have to do some estimates. So in some of the cases, I will do L2. Okay, yeah. So why I say this thing here? So I want to use a lot this estimate. So we have it here, we have it here, and here. And these two other terms are different in the sense that they don't have the difference of the modifier. This last one here will vanish as usual because this is for this we have inner product with U epsilon minus U delta. So we will have again gradient of a function applied to the same function once that we move this to the other side. So this term we can't forget about that. Okay, so I will put this one in L2. And now all these terms. I will first take this third term, which is the only one which is different, that doesn't have the difference of the modifier. So for this term here, I will put all the modifiers here disappear. So I will put this in L2. So we have this square times this in L infinity, the modifier disappears again. So this is just bounded by the gradient of u epsilon in an infinity. And now we have all the other terms. So this correctly, yes. Well, we have to do each one of them, but in all of them, I should obtain because I will use this estimate all the time. So I should obtain this, and now for the first one, we have all these terms, j epsilon u epsilon times in principle is L2, but because of this, H1. Now for the second one, we have the L2. So I'm going to do L2 L infinity, and the L2, because of the commutator, H1 L infinity. This is the only part that remains. L2 of this, I will take, for example, L infinity here. And for this one, L2, so H1, H2. And H2 is okay because this is still less than S. S was bigger than 2. So all these terms are bounded by the HS norm, all of them. HS norm squared. And for this, we already had a uniform bounds, so this was controlled by the initial data. Yeah, and we are basically we are done. We can now use Gromwell. So let me just write the final statement. We have that this is less or equal to some constant. This was bounded by the initial data, so this is just some constant. Plus mean epsilon delta. Okay. And now apply Gromwell and conclude, because also for the initial data, so we repeat the same estimate that we are using all the time. So for the initial data, we also have an epsilon and a delta. So all the terms are small. So we conclude that it's Cauchy. And okay, I'm going to stop because it's the time. But yeah, so for the next day, because I will prove the existence and uniqueness of a strong solution to Navier-Stokes, the proof is almost the same. So I will not do almost anything new. I will just point some of the differences, and I will do a step 5 that I haven't done today, showing that the limits of the equation.